Today's lesson is a little bit long in its name, but modeling situations and evaluating algebraic expressions. Those two go really hand in hand with each other. Modeling situations is kind of a way of saying something that a lot of us have grown up hating, and I actually used to hate them also, and that would be word problems. And you know why I hated them? It's because when I was growing up, I was taught not to trust myself. So today's mindset message is to trust yourself. The fact is, when you're learning something new and you have to think for yourself, it can be confusing, and I think the confusion is what we don't like. Here's the thing, many of you have been trained from when you were growing up that in math class you should know exactly what to do every time the teacher asks you something. But that's not really how math is, and especially not in high school. And this might be something really hard for you to shift, but we'll work on that over the year. Okay, right now it's important that you learn to trust yourself, because I'm going to ask you often to think for yourself. I want you to think for yourself. God created us with brains to think independently and think for ourselves and make sense of things ourselves. Math really does make sense, but learning new things, especially math, can be really confusing. I learn math on my own all the time, and I get really confused on things, and yeah, that even gets frustrating sometimes. But we want to make sure that we push through and fight through, because it's really satisfying to work really hard to understand something and finally understand it. So for today, I'm telling you to please trust yourself. Our learning goals are to write and evaluate algebraic expressions and to use variables and expressions to represent situations. That's what we mean when we say modeling situations. So if I have some sort of situation and I want to use maybe an expression or variables to actually represent what's going on. Your prior knowledge for today, you should look back or remind yourself how to calculate the area of a rectangle, and then remembering number tricks and order of operations from our recent lessons. So let's go ahead and dive into a situation that we'll use algebra to model right now. Dive right into a situation that perfectly exemplifies the topic for today. I want you to go ahead and read this through. I'll talk you through with it. And I want you to pause the video and do each of one of these things to the best of your ability. And now remember, often I'm going to ask you to think first yourself and try to do it yourself first, which is why I say trust yourself. It's really important that I'm teaching you to trust yourself if you ever lost that, okay? And it's so important. It's one of the most important things you'll get out of taking my math classes is learning to do that. You'll get better test scores and you'll just be much more confident, but you've got to kind of let go of that fear of the unknown and starting not knowing what to do. Maybe you know what to do for this one, I don't know. But still, it's going to be okay. So I want you to work on A and B and C. Okay? So you can go ahead and read this. We have a rectangular garden that's 5 feet by 10 feet right now. But let's say, whoops, I said I'm. It's you that has the garden. You are thinking of adding more to the length so that you have more space to plant things. Okay, so go ahead and pause right now and answer these to the best of your ability, and then we'll talk through them. Okay, I hope you've really spent the time to work on these yourselves, and it's okay if you have to look up and remind yourself about the area. So I'm going to do something here. I'm going to use a couple of colors, but on the side I'm going to just draw a diagram here of our garden, because we'll use this diagram for these other ones. So right now this is 5 feet and this is 10 feet. And it says, what's the current area of your garden? Well, if you remember, the area is the length multiplied by the width. And I want to remind you what area is in the first place. Area means how many square units. So in this case, it would be square feet. How many square feet can actually fit perfectly inside of the space there? Well, the nice thing about a rectangle is you can fit an even number of squares inside of there, right? So if each of these is 10 feet long and there's 5 rows of them, then it makes sense that we multiply length times width. So the area is going to be 5 feet times 10 feet. Often I'm going to leave these units out until the end, but you can also write them in the middle here. And that's going to give me 50 square feet. I want you to remember that area is measured in square units. So our units here are feet. And it's because it's really saying how many of those little squares can we fit in that space, okay? So the area is 50, but specifically 50 square feet. Let's get to the other ones. It says if you add 2 more feet to the length, what's the new area? Well, hopefully you drew a diagram yourself. Maybe you did it in your head, but drawing diagrams is a really important problem-solving strategy that's really helpful. So if I put 2 more feet onto that length, then what would the new area be? Because really our whole problem is revolving around this idea of adding length onto my garden and then seeing what's my new area. Am I going to have enough space to plant what I want to plant? So, different ways you could have done this calculation actually for part B. You maybe just realized that that turns this into 12 times 5. I'm going to leave the units out like I said. I'll put them in at the end, and that's acceptable. So this now has become 12 feet times 5 feet. Well, that might be easier to think of. I don't know if you thought of this or not, but I like to think of this as still having my original 5 times, or 10 times 5, whatever you want to do. But then I have 2 times 5 on top of that. So this is a really interesting thing. The 12 is actually 10 plus 2 times 5. But again, this visual helps us see this is the same thing as saying 10 times 5 plus 2 times 5. And in fact, actually, I might even put this as green so you can connect that with the diagram up here, right? So this part here represents 2 feet by 5 feet. So that guy's area is another 10 square feet we've added on, right? So this becomes, in the end, 50 plus 10, so 60 square feet. And again, this may seem a little bit slow for you or whatever, but I really want to point out that we could find the whole area with just one single multiplication. 12 times 5 certainly is 60, but there's many ways to think about how these numbers break down. We could think of it as our original 10 times 5 plus 2 times 5, and that's actually really helpful. Okay? Either way, that's 60 square feet. Now this is where algebra becomes our really good friend, okay? Now my guess is, as you are tackling part C, now maybe you need to rethink about A and B, and you can go ahead and add into your notes if there's anything that you missed or didn't think about. I would definitely record this part because it's likely you maybe didn't write it out exactly in that way. But now that we've got A and B and you've understood those two, if you didn't quite understand C or figure you knew where to go, maybe you now pause again and you try to do C. And you might test different numbers, right? 2 feet, well that wasn't quite bringing me to 60 square feet. So maybe 3 feet or 4 feet or however much. Does that make sense? Well, let's take a look at this one then. It might be helpful for us to just go back to our diagram, and this, I guess, oops, let's use green. What I'm going to do is I could just put a question mark right there. Isn't that really what I'm wondering? How much should I add on to this so that my new area becomes, what did I say I want? 75 square feet? Well, for now, I'm not going to tell you there's any one way you have to calculate this. What I will help you see right now is that no matter what, we have our original 50 square feet. And that's just like what we had here, right? This guy was 50 plus whatever my extra is. And in this case, we realize that this can be anything we want. So I've used this in the past. I'll use a little empty box because that represents, well, any number could go in there to extend that length. But no matter what, the area of this extra rectangle part there is going to be something times 5. So I have this, and this is the cool thing. This right here is essentially what we call an expression. So we're going to go ahead and introduce to you a new vocab word that's really important right now. So this box right here that can have any number I want in there to represent the length I'm adding on to my garden actually has a vocab word associated with it that, again, you're probably familiar with. Variable. We use variables to represent changeable values in a situation or expression. Sometimes we also say changeable or unknown. Sometimes we don't know what that's going to be. And that's actually just like situation number in part C right here. Because it says we want the area to become 75 square feet. How many feet should we add to the length? So when it says how many feet, that represents, oh, well, we know that this length is changeable, and right now it's unknown what we want it to be, so that we bring the area up to 75 square feet. So this is really important, this word, but I want you to realize it's not necessarily always just unknown. It also represents the fact that it can be changeable. And if you think about our number tricks, remember the very first step is always choose a number. And that right away tells us that we could choose any number we want. I mean, unless it told us otherwise. But so far, that's been the case, right? And that's where, when it says choose a number, that actually ties in with a variable. Now, you probably know that we don't usually use these empty boxes to represent that. Well, the fact is, at some point, mathematicians had to decide, well, what are we all going to agree on so that we don't confuse each other as a symbol to use to represent something that's unknown? We could certainly have used like boxes like this, like shapes, but what if I have multiple unknown pieces and, you know, I kind of run out of shapes. There's squares and triangles and circles and things like that, and they're also not always the easiest to draw. So instead of those shapes, they decided, oh, we're just going to use letters to represent those unknown pieces or changeable pieces. And I know people love to make jokes about, why are you bringing the alphabet into numbers? Well, it's because we needed to use something to realize that numbers can be changeable depending on situation. So it's really not a bad thing. So instead right now, I'm going to go ahead and use our traditional number that's used and call it x instead now. So up here in our question mark here, that is now going to be x. But remember, x just means that's unknown or changeable. All right, so really, we've actually created something here. This guy right here is an expression. And if you think about it, we actually want to know, when is this going to get up to? Now, when I say when is it going to become, okay, that's where we use the equal sign. For now, I'll just say become, and then 75 is what we are asking, when is it going to get there? Now, don't you worry right now. This is not focused on solving equations at this point, because we have other things to get through in this lesson. I'm just showing you a situation where it's important to realize there's a changeable or an unknown piece, and when an equation would actually come into play. So there's two things here. This part over here is simply an expression, and this is like asking a question when we're going to get to a certain place. This whole thing here is an equation. So there's a difference between an expression and an equation, because if you have an equation, it's going to ask us, when are we getting to some specific place, right? When do we become something? So we'll get more to that later. You don't need to write that any definitions for those down right now, just for variables, okay? Now, you probably want to get to the actual answer to this question. Sure. So we're not going to actually take this as an equation and solve it right now. I would trust you, and hopefully you trusted yourself, to play around with this enough until you got something that worked. Well, here's the cool thing in my mind. If I know that right now there's 50 square feet, so this is one way to solve this problem. This guy has an area of 50. Well, if I want to bring it to 75, that means I want this to be 25 more, right? And again, maybe you did it differently. Maybe you did do an equation. That's great. No matter how you did it, it's totally okay. But for now, this is how I would think it would be good to think about. And if that's 5, what should that be? Oh, that should also be 5 feet. So that 5 times 5 gives me 25. So like I said, no matter what you did to actually solve this problem here, the actual answer for this is going to be, I should add 5 more feet. Now let's jump into a few other examples. This is really the main meat of the lesson, but we're going to dive into some specifics with number tricks and things. So what we just wrote down in 1C involved an algebraic expression. It's just a mathematical phrase, like an expression in English. It's the same, it's just a phrase that uses operations to combine numbers and variables. So we just saw an example of an expression, but then we actually asked, can it be equal to something, okay? So I want you to remember that an expression is just a phrase, okay? It would be really helpful for you to specifically think of it like that, okay? It does not ask any questions, but you could ask questions about that phrase. Now, if that's a little confusing, don't worry too much right now. Just make sure you understand this definition at this point, because we'll talk about it more later. So I want you to go ahead and do these next ones on your own. If you still feel like you're having trouble understanding what to do, maybe you can go through the first one with me and then pause and try to tackle the rest yourself. But hopefully you can do all of number 2. Now remember, this is matching. So you have A, B, and C, these number tricks, and each one of these is in a different order that correctly matches one of those above. And then this is asking for you to write your own. Okay, so go ahead and pause right now. All right, let's go ahead and take a look at this together. Let's see, I'll use green for the answer so it doesn't get confused with the red. So remember that each of these things, even though they involve the same numbers, they're all doing the calculations in a different order. Actually, it's the same numbers and the same calculations. So it's kind of up to you if you'd rather just like think about writing the expression, or maybe you want to start with one of these and then just say it out loud what the order is. I'll do that. So here's parentheses mean do this first, right? And then inside of here, I need to do the division first, right? So this is choose a number, divide by 2. And honestly, maybe we already have our answer at that point. Does that one of them have a first step, divide by 2? Oh yeah, it's that one. So B must match with 1, or I. Okay? But it's divide 2, then add 3, and then after that, multiply by 5, and that matches. So let's tackle the next one. This one here, let's see. Remember, the division symbol is a grouping symbol, so we need to do everything up top first. And there's parentheses. So this is choose a number, add 3. Looks like that one. Multiply by 5 is next. And then after all that, divide by 2. So yep, it looks like that one matches A. And there's only one left, so you obviously know what it is, but let's still talk through it. This says choose a number, and there's no parentheses, so I'm going to do the multiplying first. Multiply 5, then add 3. And then in the end, divide 2, just like we divided 2 in the end there, but this order was switched around. So this guy right here matches with expression number 3. Let's tackle example 3 here. So using n as your starting number, we used x here, but any letter is okay. Write an expression. So let's go ahead and do this. So choose a number, subtract, let's think it through first before we tackle writing it. Subtract 9 before multiplying by 2. I think you and I both agree that we're going to need to use parentheses because we want subtraction before multiplication. So if we choose n as my starting number and subtract 9, but then I want to multiply that by 2. Now we often put the number we're multiplying by in front, even though if we go in order it seems to make sense to put the 2 in the end. It doesn't matter, because if you think about multiplication, right, we know that it doesn't matter which order we multiply in. So I'll just put it up there like we often do. And then add 10, subtract 3. Do we have any special order that we need to deal with? Nope, adding and subtracting are all on the same level. So it's just add 10 and minus 3, and voila, there's our expression. So you can check your own work on that. Now B is interesting because it says, can you find an easier or shorter number trick that is actually equivalent to this? There might be something, if you just look at this expression, that light bulb comes on your head. There's something right away that's pretty easy to make this even shorter. I see that these two could just be combined into one thing, because if you see plus 10 minus 3, 10 minus 3 is just 7. I could have just written this like that. So these two could actually combine just to be saying add 7. So that's interesting that even though this is correct, this is also correct, and even though they're technically different steps, they actually represent the exact same result, no matter what number you start with. So that's interesting. Now, some of you maybe even went further than this, and you simplified this using other methods you've learned, like maybe distribution, which you could go further. But we're going to save that because we're going to learn about that topic a little later. There's definitely even more we could do to make it fewer steps and simpler. But that's just some food for thought to get you thinking. Let's run through a few more examples before this lesson. So let's end things off today with one more vocab word, or a couple actually, and then 2 more examples. So if you think about example 3 that we just saw, we noticed we had 2 expressions that were always equal to each other. So sometimes the equal sign is not like asking a question, like when do we get to this ending point? But sometimes it's just a statement saying that this thing here is always equal to that thing. Okay? So our definition says if there's a way to write an equivalent expression. So we call this expression and this one equivalent expressions because that means they're always equal. But with fewer steps. So if there's a way to write an expression equivalently with fewer steps, this is what's called simplifying the expression. And I did mention actually that there are even more steps we could take this one to simplify it further. Basically, there's a way to go all the way before you can't go any further. That's technically fully simplifying. But we will get into that more later and focus on that at another time. So our last 2 examples, they won't be too long. 4 says use your calculator to evaluate the expression here. 4 times all of x minus 3 plus 12 and then entirely over 2 for various values of x. We're going to actually jump to the paper and I'll show you how to use your calculator to evaluate and do calculations faster than you might know how to use your calculator. Remember, this calculator is a very useful one to have in order to do this, so that's what I'm going to use. And then we'll jump into number 5 after that. So let's jump on over to our paper and then we'll come back and finish. Okay, so here we are, and I'm just going to share with you how to use this calculator I've asked you to have in class to help us with evaluating, which you might think of it as plugging in numbers to an expression and see what comes out. So I've labeled this table in, out. Now, of course, you could label it the in as x, and the out is actually that whole entire expression. Helps us calculate what comes out. So I'm just going to choose a few myself, and then I'll ask you to just, in your own notes, have your own numbers that you've calculated. The cool thing about this is, remember we talked about how choosing numbers wisely to plug into things. So for example, in the end here, you notice that we're going to end up dividing by 2. Maybe we need to be thinking about trying to have this number divide nicely by 2 if you want nice numbers. But we don't always have to have nice numbers. The cool thing about our calculator is that it'll do for us, even if it gets kind of ugly. So I'll just choose a random number. I chose 6. Now, let me show you how we'll do this on our calculator. You'll notice that this whole thing up here needs to be done first before we divide by 2. Now, it's actually maybe a little more helpful to think about if instead of the division fraction bar, if I actually had the division symbol here. And so if I cross this out, we would have to put parentheses there to say divide by 2, because we want everything divided by 2, right? And your calculator thinks in the same way. So here's the buttons to push. I'm going to actually push 4, and your calculator knows to multiply if you don't use the actual multiplication symbol. And there's where our input goes in. So it's going to be 6 minus 3. And then I forgot, didn't I? I need to put parentheses around everything because I need to add 12 and then close the parentheses off. Now here's the cool thing. You can use the division symbol right here if you want, or I'll press delete. That just gets rid of that. If I press like AC right here, it'll erase everything. So the division symbol's fine, or you can push this button right here. It's great. It actually puts it as a fraction, and then I could type 2. And you just press equal, and it does everything for you. So in goes 6, and out comes 12. How about the number 1? I don't know. I chose 1 because if you think about my first step as -3, it's going to make a negative happen in there, which is kind of an interesting thing. But again, we're kind of focusing on our calculator use. We're not going to do it all out in our heads right now, which is good practice, but for now we don't need to. Now here's the cool thing about this calculator. We can go back up, actually back. If I push the left arrow, I can go back into here and just change one single number in this, so I don't have to retype it in every time. I'm going to press delete. And then let's just replace that with 1, and out comes, boom, 2. So when 6 goes in, 12 comes out. When 1 goes in, 2 comes out. I thought of another number. What if I do like a decimal, like 2.5? That's kind of an ugly number, right? Well, let's do the same thing where I go back and up, and we'll go back here, delete that, and put 2.5 there as my starting number, and then equals 5. Wait a minute, there seems to be maybe a pattern forming in this. Why don't you, we're not going to finish talking about this. We're going to bring this problem back in a later lesson. But why don't you go ahead and do, let's say, 3 more of your own here and see if you can notice any patterns with the in and out column. And we will revisit this, like I said, later. Let's jump to our last example. Number 5. So Hurricane Maria struck Puerto Rico in 2017. And a lot of shelters had to be created that provided food and beds for victims. Now, these numbers aren't actual numbers, but they could be. So what we want to do, like it says, is find patterns in the numbers. So if we look at the day right now, maybe isn't as important, but we're just saying these are different days. I could call it A, B, and C or something. So those numbers aren't really as important. Like I said, let's actually call them A, B, and C. But rather, I want you to think about, based on the number of people, do you notice any patterns in how many beds are needed and in how much food is needed? So if you look at those numbers really carefully, you can pause if you want, if you need to look at it for a moment, and then we'll look at that, and then we'll write some expressions here. Okay, so hopefully you realize every time you have a number of people, there's 5 extra beds more than the number of people that is required to get there. What could be the reason for that? Maybe it's just that you want to have some extra beds just in case, you know what I mean? Maybe if they break or whatever happens. And what if you compare the pounds of food needed to the number of people? Hopefully you realize that this ends up being, and actually I'm just going to write P plus 5, and in fact it's all plus 5, so my actual expression here, I'll put my answer here, is P plus 5. That's for the beds. Now for the food, hopefully you realize if we take this and we multiply it by 2, okay? Now we could write P times 2, but you probably realize that, like I said, it's kind of standard to write the number before the variable. So 2 times the number of people will get me how many pounds of food that I need. Okay, and that's really everything for this lesson. So happy math. Don't forget to trust yourself, and I'll see you in the next lesson.